All right, here are the notes for section A2, deals with areas in the plane. So we start with the area between two curves. So if f and g are continuous functions with f of x greater than g of x throughout the interval, which means if you look at the graphs, f is always above g. Then the area between the curves y equals f of x and y equals g of x from a to b is the integral of f minus g from a to b, or area, so f of x minus g of x. So find the area of the region between y equals secant squared x and y equals sine x from 0 to pi over 4. So here's what that would look like. So the first thing we need to figure out is which graph is above the other one. Secant is actually always more than sine, so it's the upper one. So this is our f of x function. This is our g of x function. If you're unsure, graph the two of them and compare.
Hello, high school bell toll.
So our bounds are 0 to pi over 4. So this will be secant squared x minus the sine of x. So we do the antiderivative. The antiderivative of the secant squared is the tangent of x. The antiderivative of the negative sine is the positive cosine of x, evaluated from 0 to pi over 4. So that's going to be the tangent of pi over 4 plus the cosine of pi over 4 minus tangent of 0 plus the cosine of 0. And we work all this out. This is 1 plus root 2 over 2 minus 0 plus 1. So this is 1 plus root 2 over 2 minus 1, or just root 2 over 2. They may have the case where the curves intersect. So find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. So this we will have to look at the graph. So let's see here. So here's our parabola over 1, 2 down. So there's our parabola. Y equals negative x would be this line here. So area enclosed, we're talking about this area in here. So the parabola, if you look at the graph, is our f of x. This equation is our g of x, but we need to figure out the bounds. We need the intersection points. So looks like there's a point here at negative 1, 1. And there's a point over here, which is going to be at, let's see, algebraically, if you want to figure out where they're equal, you actually set the two equations equal to each other. So this is 0 equals x squared minus x minus 2. So x minus 2, x plus 1. So they intersect where x is 2 and where x is negative 1, which we already got that one. So this point over here would be 2 comma negative 2. So when you build our bounds, it's the x values that matter. So x is negative 1 up to x is 2, because our derivative is, or our antiderivative is dx. So the upper curve minus the lower curve. So this is from negative 1 to 2 of 2 minus x squared plus x dx. So if we do the antiderivative, that would be 2x minus 1/3 x cubed plus 1/2 x squared from negative 1 to 2. But I'm going to let my calculator handle that. So we got 2 minus x squared plus x from negative 1 to 2. Gives us an area of 9/2. Okay, so example 3. Find the area of the region enclosed by the graphs 2 cos x and x squared minus 1. Okay, so we need to look at the graph of this guy. So, wow. Let's look at the graph on the calculators. I want to try to draw this. Well, we can. So 2 cosine x is going to do something like that. X squared minus 1 is going to do something like that. So we need to find those two locations. This function is our upper one, so it's our f of x, which means this one is our g of x. The calculator will let you find the intersection points. So We're going to graph the two of them to cosine x. We're going to graph x squared minus 1. And then g-solve intersection points. Now all that really matters is the x value. So this coordinate is at negative 1.27, which means this one's probably a positive 1.27. Yep. Positive 1.27. So, let's see here. So we would have the antiderivative from negative 1.27 to positive 1.27 of 2 cosine x minus x squared minus 1. Don't forget those parentheses there, because when you clean this up, that 1 is going to switch to being a positive 1. And then this would just go in our calculator. So 2 cosine x minus x squared plus 1 from negative 1.27 to positive 1.27. So this area comes out to be about 4.99. All right, there's the case where your functions can change boundaries. So which one is above and which one is below. So find the area of the region R in the first quadrant that is bounded above by this and below by the x-axis and the line, y equals x minus 2. So if you look at our graph, so y equals root x does something like this. The line x minus 2 does something like this, when that's positive 2. So we're looking at just this area. So there's actually two shapes here. We have to split it here because the bottom curve is different here. So from 0 to 2 on the x-axis is the bottom and the curve is the top. But from 2 to whatever this point is up here, which is probably 4, or 4 comma 2, we have to do two separate integrals. So we have region A and region B. So for region A, which is from 0 to 2 on the x-axis, our upper curve is root x, and our lower curve is the x-axis, which means it's just 0, so we can leave it off, minus 0. And then we have region B, which starts at 2, goes to 4. The upper curve is still root x, but the lower curve is now x minus 2. So we need to figure out these two values and add them up to put them back together. So for the first one, from 0 to 2. So this region has an area of, called about, well, actually we'll just do this all in one step. Antiderivative of root x from 0 to 2 plus the integral of root x minus quantity x minus 2 from 2 to 4, 3.3 repeating. So, which is 10/3. All right, you don't have to integrate with respect to x. You can also integrate with respect to y, which makes it a little bit easier if you don't want to have changing things. So find the area in example 4 by integrating with respect to y. So we need to solve these equations. Y equals root x would become x equals y squared. Y equals x minus 2 would become x equals y plus 2. So in this case, you're looking for farther to the right versus the upper one is farther to the right. Since we're spinning about, we're measuring from the y-axis, so this one is now the farther one away, so it's going to be our first minus the second. Now our y values range from 0 to 2, the y value here at the intersection. This one is always to the right, so y plus 2 minus the one on the left, y squared, dy. Now your calculator doesn't care about what variables you use. It's going to work the same way. So this is going to be half y squared plus 2y minus 1/3 y cubed, evaluated from 0 to 2. So if we plug 2 in, we get 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 cubed. So f of a minus, now f of b is just going to be 0, so I'm going to ignore it. So this is 1/2 times 4, so that's 2 plus 4 minus 8/3. So this is 6/3 plus 12/3 minus 8/3. So that's 20/3. I've gone off somewhere. So I should get the same answer. I should get 10/3 again. So where's my mistake? Oh, but that's 18/3. There we go. Okay. Alrighty. So we got that. Which brings us to example 6. Area enclosed by the graphs y equals x cubed and x equals y squared minus 2. So let's see here. So if we graph these guys, y equals x cubed, so something like this. This is a sideways parabola going this way. So this one is going to be our f of x because it's always the one to the right. This one's going to be our g of x. It's always the one to the left, but I need to rearrange this. X is equal to the cube root of y. And then I need the y values of those intersection points. And those graphs intersect, let's see here. So this is at -1. If you let your calculator solve it, you get this one to be about 1.79 positive. So from -1 to 1.79 of the rightmost function, so cube root of y, minus the leftmost function. So look like this. I'm gonna let my calculator handle it. Now remember, your calculator doesn't care about the variables, so you can just type x's in even though we are using y's. From -1 to 1.79. And we get an area of, oh, calculator's thinking about it. This would equal 4.21, we'll call it. Now you could also do, you could rearrange this to solve it for y, and then you'd have upper here. The problem is this bow is kind of back, so you don't want to do it that way. It's more cleaner to do the right and the left versus top and bottom. You're looking at that area there. All right, it is possible to save times if you know the geometry formula. So find the region example 4 by subtracting the area of the triangular region from the area under the square root. So what that's saying is, instead of, because we had this graph, instead of doing it as 2 separate areas, we could just do this arc and subtract off the area of that triangle. This triangle is 2 units wide by 2 units tall. So we could do all the way from 0 to 4 of root x minus the area of the triangle, 1/2 base height. Oops, sorry, dx there. So this would become nope, 2/3 x to the 3/2 from 0 to 4 minus 2. So 2/3 4 to the 3/2 minus 0. So when I plug 0 in, I get 0 minus 2. So 4 to the 3/2 times 2/3. So this is 16/3 minus 2, which is 16/3 minus 6/3, which is 10/3. So if you see a shape that you know an easy area formula for, you can use that to solve these problems as well. That brings us to the end of the section.